Okay, in our first lesson in geometry, we're focusing on patterns and reasoning. So as you're setting up your Cornell notes, this is section 1.1, patterns and reasoning. And our essential understanding for this is that students will identify patterns in order to make conjectures. And that's our first learning goal for this entire unit. So we'll get that set up on the page in our Cornell notes. So this is actually a really quick little lesson, not a lot of notes that you have to take here, but some of the things that I want to focus on are inductive reasoning and conjectures. So even though you weren't in class students participated in an activity where they had to look at a sequence of terms and try to figure out what came next. So anytime you're looking at a sequence of terms, what you're really doing is using inductive reasoning when you're trying to figure out what's the next term in the sequence. So inductive reasoning is a type of reasoning that allows you to reach conclusions based on a pattern of specific examples or past events. So in other words, you're looking at stuff that's already happened and you're trying to say, okay, well, based on what's already happened, what do I think is going to happen next? And that's the process of inductive reasoning. So let's look at an example. If I had the sequence 5, 9, 13, 17, and I asked you to find the next two numbers in that sequence, we'd be using inductive reasoning. So if I look at the difference between those numbers, each one is a difference of 4. In other words, 5 plus 4 is 9, 9 plus 4 is 13, 13 plus 4 is 17. So to find the next two numbers in the sequence, I would add 4. So 17 plus 4 is 21. 21 plus 4 is 25. And that's all there is to it. Now, for this lesson and in this part of our learning goal, there's actually two different types of sequences you're going to work with. This is called a numerical sequence. But we could also look at a more geometric sequence. And actually a geometric sequence can mean a couple of different things. But since this is geometry, we're talking about a sequence that's based off of some shapes or something like that. So here's a really simple geometric sequence. Let's say that the first term was a triangle, and the second term was a square, and the third term was a pentagon. And I asked you to predict, well, what would the next two terms be? Well, I can see that each of these shapes are different. I know that they're different because they have a different number of sides. A triangle has 3 sides, a square has 4 sides, a pentagon has 5 sides. So I would suspect that the next term had 6 sides. That's a hexagon. And I would suspect that the next term after that would have 7 sides. And a 7-sided figure is actually called a heptagon. It's hard to draw, but we'll try it out here. 1, 2, 3, 4, 5, 6, 7. All right, well, that's pretty close. That's a good 7-sided figure there. And then that sequence could continue. So looking at a pattern, making a conclusion about the pattern based off of what's already happened is inductive reasoning. Okay, so our second vocabulary word for this lesson is conjecture. And any conclusion that we reach using inductive reasoning is sometimes called a conjecture. So let's maybe look at an example of this. In the last sequence that we just looked at, we found the next term by first finding a pattern and then using the pattern to make a conjecture about the next term. So a conjecture is kind of like a conclusion or a guess. It's not just any old guess, though. It's not like say, hey, guess what number I'm thinking of. That's not really a conjecture. It usually has to be based off of something that we've already looked at, based off a pattern that we've seen. So let's take a look at an example. Candace examined 5 different examples, and then she came up with this conjecture. She said, if any 2 positive numbers are multiplied, then their product is always greater than either of the 2 numbers. Okay, well, remember what product means. Product means multiply. So what Candace is saying is that if we take two numbers, for example, 3 times 2, and we multiply them together, we get a number like 6. And what she's saying is that 6 is greater than either of the two numbers that we started with. And in this example, that would be correct. Another example might be 4 times 5. And 4 times 5 is 20. And 20 is greater than 4, and it's greater than 5. So this is another example where her conjecture is correct. However, she's not always correct because you don't always have to multiply by numbers that are bigger than 1. So for example, what if I took 4 and I multiplied it by 1/2? Both of those are positive numbers. That was part of the condition. We had to have positive numbers. But when I multiply them together, 4 times 1/2 is 2. And while 2 is bigger than 1/2, it is not bigger than 4, so her conjecture is not always correct. So we're going to make a lot of conjectures in geometry. We're going to look at things that are happening and try to make some reasonable guesses about what that means. And then we're going to test our conjectures, kind of like we do in science with a hypothesis. You make a hypothesis, you devise an experiment, you perform the experiment, you look at the results and see if the results support your hypothesis. We're going to do the same thing in geometry. It's like science and math. We're going to look at some examples, we're going to make a guess, and then we're going to test our guess to see if it's true. Okay, so that's it for the first section. And then in the next section, we'll start to apply these ideas of inductive reasoning and conjectures.